Welcome to Understanding Electricity. This is episode 2 of the series called Types, Generation, and Delivery. In the last episode, we discussed what electricity is, which I hope you found entertaining and enlightening. However, a comment about that. The explanation I provided only provided a general understanding of electricity, not the complex, detailed information that the study and science of electricity can provide. It is far more complex than my explanation. However, for the purpose of obtaining a basic understanding, it fulfilled the need. I'm going to apply this same approach for this video. It'll give you a basic understanding without diving into the complex intricacies of industrial production. Most people believe there are two forms of electricity, and we generally consider each to be separate from the other. One we call a battery, and the other the wall outlet. The battery provides a form of electricity called direct current, or DC. The wall outlet provides alternating current, or AC. They are both electricity created by the flow of electrons. They just present themselves in two different formats. Most people believe a battery won't hurt them, while they know that the wall outlet can. Well, that's not exactly correct. In practical everyday terms, it's correct enough. Here's why. The everyday household battery is low voltage, and it's the low voltage that keeps you from being hurt, even though batteries can store a large amount of power. For example, the battery in your car can produce over 100 amps of power. That's a dangerous amount, more than enough to crank a cold engine and more than enough to stop your heart. However, it can only force that potential with 12 volts. That's pretty low pressure. And the flashlight battery is only 1.5 volts. These low voltages are not enough pressure to overcome the natural resistance of your skin to electron flow. It's why you don't feel anything when you touch the top of a 9-volt battery. With a car battery, it's the same thing. But that doesn't mean that given the right circumstances, it won't hurt you. It can, especially if you short the poles with a wire or a piece of metal. Remember, that battery has enough power to crank over a cold engine, so don't be cavalier about it. Use proper caution when you work with electricity. The battery holds a charge of free electrons, and it releases electrons flowing in one continuous direction. Since the electrons are negatively charged, they leave the battery at the negative connection and return to the positive connecting point. That is the direction of flow for direct current. The electron flow is contained by the wire conductor, which is called a circuit. The lamp in the circuit glows as proof that electrons are flowing. If the circuit is open, as we see in this graphic, the electrons cannot return to the battery and flow stops. If the electrons stop flowing, there is no electricity and the light goes out. With alternating current, the principle is the same, only the format of the electricity is different. With alternating current, the electrons do not flow in one direction, but jump back and forth. They are in a state of constant oscillation, which means they alter their polarity direction. This switching back and forth is why it's called alternating current. The method allows electricity to act and perform like a jackhammer, constantly pounding, then pulling back to take another blow. That method is quite powerful and quite successful at operating practically every appliance and motor we have today. Alternating current is not found in nature. It is a man-made creation. In North America, the frequency in which the oscillation occurs is 60 times per second. That frequency is called hertz. The wiring example you see is called a closed circuit, meaning the conductor loops from the source, which in this example is the energized connector in the outlet, also referred to as the live or the hot wire, back to the return, which is called the neutral. The neutral is the ground return for the electrons. Again, the lit bulb is proof that electrons are moving. Now here's something to pay attention to. As you can see in this next graphic, the circuit is incomplete, causing an interruption of electron movement. And without movement, the bulb will go out. This is called an open circuit, and it can be dangerous. Many people think that because the bulb is not lit, there must not be electricity present. Don't be fooled by that. The bulb is not lit is a symptom of a condition, not proof of the lack of electricity. As you can see in the graphic, the conductor is connected to the hot side of the outlet. This allows the entire conductor to be energized up to the point where the break occurred. This is an important point to remember. Electricity always wants to find ground as fast and as easily as it can, and it will always take the path of closest and least resistance to get there. If you were to touch that hot wire while your other hand touches a ground source, you would become the conductor. Electricity entering one hand and exiting the other will flow directly across your heart as it heads for ground. In this case, through your arm and leg. It can easily stop your heart. Don't put yourself in that position. Always assume the wire is hot until proven otherwise. Unless you have solar panels or wind turbines, more than likely your electricity will come to you from a utility company. This could be your city or regional provider. Regardless, a power station generates the electricity, and transmission wires are used to move the electricity around to where it's needed. In the simplest of perspectives, water is used to generate electricity, either cold water, such as that behind a dam or a reservoir, or it will apply hot water in the form of steam. The energy of either one will spin the turbine, which creates the electrical potential. Cold water generation is called hydroelectric production. The water pressure flows over the turbine blades, turning the generator. With steam generation, a heat source is needed to boil the water and create the steam. This could be any heat source, from geothermal to coal or natural gas to nuclear. The object is to spin the turbine. The electricity from the turbine generator is transferred to transmission lines, which carry it to where it is needed. These are high voltage lines, some carrying over 50,000 volts. However, that level of voltage is not practical to bring into the house, where the standard voltage is 120 volts. That means before entering the home, a transformation must take place to reduce the voltage. That is the function of a transformer. The transformer utilizes a phenomenon called magnetic flux, which is another fascinating thing about the universe. The transformer works like this. When a wire is energized with voltage, an electromagnetic field is generated around that wire. If you coil that wire around an iron core, it will magnetize that core, creating an electromagnet. You can see these in use in the scrapyards to move metal around. We adapt this effect to create a transformer. If you coil a separate wire onto the same core, when the primary coil is energized, the iron will magnetically flux. This will cause an electron current to be induced within the secondary coil. It is this process by which the high voltage is transformed to the standard household voltage. The fewer the wraps of the secondary coil, the lower the induced voltage. A calculation will determine how many primary and secondary wire wraps are required to produce the desired output. As a standard, a single transformer offers two 120-volt lines to the house. Each line will conduct up to 100 amps of current. Each supply line is called a phase. Just to take note here, because of the placement of the windings around the core, each phase is induced at a slightly different time. As seen in the graphic, the top output coil is induced for the secondary coil. This is a known characteristic of multiple output transformers. So what does this mean to us? Well, not much, really, as long as we understand it and account for it. For example, your central air conditioner system likely requires 240 volts alternating current to operate. Since the utility transformer is only providing two 120-volt lines to the house, we send two 120-volt lines to the air conditioner. The combination creates the needed 240-volt input. The thing to remember is that the two lines service the same appliance, and therefore must come from the same phase coil of the transformer. Years ago, that wasn't much of a concern, but with today's electronics being embedded into our electrical equipment, it's becoming more important not to mix the phases. Let's have one more look outside. There are three physical lines coming in from the transformer on the pole to the house, two separate 120-volt lines, and one ground wire, called the neutral. The neutral is connected to a wire that runs directly to the physical ground. You can see it here. This is the return ground, literally a return to the ground. The service lines are attached to a receiving house mount and are routed through a conduit to the electrical meter. From the electrical meter, the lines are terminated in the house electrical distribution panel. We'll have more about that in the next video. This concludes video 2. In video 3, we'll cover the breaker panel and distribution in the home. Thank you for watching.